Thank you. Good morning, everyone. It's a pleasure to be here. My name is Charalampos Triantafyllidis, and I'm a research associate in Imperial College London and University College London of late. I have a background in computer science, and I'm going to be presenting collaborative work that we did with a series of teams. The technical team in Imperial College, including myself, which was led by Professor Neil Issa, the Institute for Integrated Economic Research, and the engagement and platform delivery team, which was the Ecological Sequestration Trust. So in terms of the Future Cities Africa project, which was funded originally by the Department for International Development, we wanted to produce a platform that actually helps sustainable and resilient decision-making on the ground. The motivation was actually to target it in the first application for the water, sanitation and hygiene sector, and to have an application in the sub-Saharan Africa region, in specific in Ghana. The reason behind it is that, as we all understand, water is essential for life on Earth, and it's at the core of sustainable development. And we could also say that, for instance, envisioning a more sustainable future without first addressing the challenges around water could probably render infeasible, arguably. And the motivation behind it was also to make the whole platform open source and non-commercial, so everyone could have access to the implementation and hopefully contribute and develop it and polish it even more further. So the name of the platform was resilience.io, and you can actually get a lot of information about it if you Google resilience.io on your browser. The basic articulation behind the implementation scheme is as shown here. It's a combination between different modeling methodologies, so starting from some scenario data, as we call it, some minimum amount of data that we need to initialize our simulation. We have the agent-based model side, which is to reflect to the outcome of the activities of the citizens of a region that we have under analysis. That in turn generates some demands in water, clean water access, and the treatment of the wastewater produced, obviously. And all of that as an output is actually an input to another module of decision support, which is the optimization side of the platform, and we call it resource technology network optimization, in order to inform the decisions in the most effective and efficient way. There's also the ability, of course, to go through these modeling approaches in turn. For instance, the output of the optimization could be the input for another scenario, for instance, based on the results and the outcomes suggested. So in terms of software, just a little bit about what kind of software packages we used. We used YAML for the input data file, which is a human easily recognizable language to represent data. And we used Java to program the whole module of the agent-based model and the resource technology optimization. And we embedded a free optimization solver, which is GLPK. And also we used the R programming language for some post-processing of the results and some visualizations that come after the optimization. So as the whole challenge that we have to tackle here is emanating from human behavior, it's actually reasonable to represent the citizens of the city region as agents that have some socioeconomic characteristics and some spatial characteristics as well. And this is what the agent-based modeling side does. It tries to render the behavior of the population in the most realistic way to understand how these demands in clean water come and how they're actually produced, and how can we actually make predictions in the future in terms of population growth and how this actually affects sustainability in this context. So to simplify the calculation method on this module, we start the simulation by having the population and the agents with their associated characteristics. Of course, we're not able to, for instance, render the whole population realistically, so we need a synthetic group that we hopefully assume that captures the differentiality of the population in a very realistic way. And based on that, we have the outcomes of the use of the clean water and the produced wastewater. And aggregating, multiplying and aggregating, we get the whole picture for the under analysis region overally. So about the optimization side, it's a formulated optimization problem. What it does is actually, given under a certain set of constraints that we have, productions, investments, flows, maybe the expansion of the pipe network as well, and given some variables as well, we formulate an optimization problem and we try to answer the question of how can we effectively allocate investments if they're actually needed to reach the desired targets. What's the associated cost in terms of capital and operational expenditure, and of course what's the environmental impact in terms of emissions in carbon dioxide. So what we do is we actually initialize the model with the current status, as we call it. So it's the allocation of the infrastructure that we have in place at the moment, the technologies that actually are used as conversion processes from one input to another. And we set the desired objectives, which, for instance, could be the Sustainable Development Goals, reaching 100% meeting demands in water and sanitation. The model tries to answer how these targets can actually be answered in the most effective and efficient way. And of course, you have the ability to tailor your use case to represent more realistically what you're actually examining. For instance, there might be some policies very specified for a region. You can incorporate that into your model to make it more realistic. There's a lot of parameters that you can actually tune in the platform. I listed some of them in the following two slides. Just to quickly go through some of them. For instance, you can specify the leaks on the flows that you have on the pipe network. You can specify the bandwidth that you have according to the type of the pipes that you have in place. Geolocalization of the multiple cells that you have that you represent in your region. For instance, in Africa, we have 15 different districts that we try to simulate. So the distance between the technologies and the associated flows also takes into account the pipe and the distance covered, and that also accumulates to the associated cost. You also have the ability to define which resources you want to have in your network. Some of them might be able to flow, some of them might not be able to flow. The associated costs in the inputs of electricity and labor as well is taken into account. And for the technology and investment side, you also have the pipe network, the admissible expansions that you might have in specific technologies or in the water and treatment network as well. So the first application was in GAMA, which is the Greater Accra metropolitan area, and we wanted to see how we infer optimal decision making in investments to reach the Sustainable Development Goals. And we did a use case using some data sets for the potable water and wastewater distribution. As you see, we used a potable water pipe network with some other technologies to treat clean water, as source water treatment, for instance, and desalination plants. And for the wastewater, we had the sewage pipe network with some other technologies, conventional and not conventional, as activated sludge, aerated lagoons, and the wastewater treatment facilities as well. So it's pretty much straightforward what these scenarios represent. We had three different cases: the decentralized scenario, the SDGs scenario, and some leakage reduction scenario as well, going from 27% to 17% in terms of leaks on the pipes. And some of the results that came out of this use study are represented here. We have lots of different indicators about the capital expenditure and the operational expenditure associated to reach these targets correspondingly. I think it's interesting to see that there's a huge difference between the operational costs from the decentralized to the SDGs on the 27% leaks and following to the 70% leaks reduction scheme. Also, we can get some information about the labor and electricity inputs as well, and of course the emissions in CO2. We also have some visual outputs from the platform to make the results a lot more digestible from the broad public, and we visualize the results coming out from the optimization solver in a different scheme of graphs. We have, for instance, the network and the expansions shown as arrows. I think that my time is finishing, so I'm just gonna show the last slide about the overall scheme of the implementation, which is the agent-based modeling side from the downside, and to the upper side we have the resource technology optimization with some policies on the right-hand side, all of it working together as a seamless working environment.
Thank you. Okay, I'll take a question up the back there, yep.
Very interesting modeling work. This agent-based model, is it capable of reproducing observed behavior? Have you tested this model, the agent behavior component, maybe not the overall optimization? Obviously, the Greater Accra region is not optimizing maybe in the way you desire, but what about the agent behavior? Are you validating that against observed behavior?
Yes. We actually calibrated the whole simulation, so it actually represents the real figures that we had from the local statistical agency in Ghana. So what we had...
Perturbations from that.
Sorry?
Historical changes.
So the data that we had was from 2010, and the simulation that we did was onwards, and we tried to match up the figures that are actually generated from that point and onwards.
So do you reproduce 2014, 2015?
Exactly, yes. In terms of population growth, the projected population growth on these years.
Yes, okay, right.
Can I, this is a related question, because actually I think what you have is actually a micro-simulation model. You don't actually have an agent-based model. And I think that is quite an issue, because with the micro-simulation model, basically your behaviour is linked to the data of the different types of agents is fixed. There's no decision making, there's just past data on linkage between particular characteristics of individuals and their resultant needs. And the problem with that is, of course, you cannot look to scenarios of radical behaviour change and different ways of behaving and so forth. And given you're looking over a quite long term, you could have all sorts of changes in wealth leading to extensive putting in swimming pools, who knows what in terms of technological change. And that actually could totally turn around your results, because actually one of the key sort of claimed benefits of decentralized systems is the ability to have a relationship between the infrastructure and the people, so that actually their behavior becomes more related to the nature of the infrastructure, so they don't, they actually have a relationship to their impacts and infrastructure needs. So you can actually, if you had an agent-based model and you were able to explore those things, you might actually find that a decentralized approach was much cheaper in terms of meeting changed behaviors.
Thank you. Well, we tried to make the agent-based modeling side as more realistic as we could, incorporating all of the characteristics that we had in our disposal, but we also tried to take into account the access that they had, people have there in potable water, or for instance, if they're commuting every day to their work, having some webinars with local stakeholders to understand the habits that people have there. When do they wake up in the morning? How many times do they visit the toilet, for instance? And try to make all of this simulation more realistic as we could.
I think we are going to have to leave that there, but I think there's an awful lot to discuss there about who are your agents, who's being modelled, and if you're using existing data for people that already have access to the network, that's likely to be quite different than the people who don't have access, who are the intended beneficiaries of the Sustainable Development Goals.